Okay, all right. Well, happy Friday. Happy Friday, everybody. Hope things are well, and good job on the midterm. And shout out to Josh for resources created. But yeah, you guys studied well, and overall the class did pretty well. If you didn't do that great, don't feel bad. There's still plenty of points left in the quarter, and then again, you're welcome to check out your exam during office hours, but no office hours today, or not on Saturday either. So, but okay, today we will look at neural networks, and we'll kind of do not the first, but just like we'll look at a classic neural network example. And it's the MNIST handwritten digits data set. So let me just show you a little bit. So if you just search MNIST data set, this is pretty much what the data set kind of looks like. It's a bunch of little pictures. So this was research kind of, for the post office, I guess back in the 80s, 90s, they had computers that were able to kind of read and recognize, printed numbers, but then what about handwritten letters, right? And so sometimes you address an envelope and you put it in the mail. And they wanted, and those used to just be sorted by hand, right? So there'd be a human who would look at it and go, okay, digit, 90210, this is going to go over to the whatever this chute over here and stuff like that. But they wanted, computers to be able to do this. And the problem is well, people's handwriting differs, right? Like we can, there's something miraculous happening in our brain where we can look at all of these different squiggles, and our brain says, hey, these are the number 3. And right, all of these squiggles, our brain is able to recognize those as the number 7. But that's a miracle in of itself. But, we're accustomed to it. That's just how our brain works. And we don't really know how our brain does it, but it does it. And we're just like, okay, well, yeah. Well, can we get a neural network to do it? And the answer is yeah, we can get a neural network to do it. Also, like our human brain, we don't know exactly how it's doing it, but it does it. Okay, and so we're gonna download this MNIST data set. I've actually already downloaded it, but you can do this too. And you would go to this website. This is so if you search for MNIST data, there will be different places where people have like converted the data into like CSV forms and stuff like that. But this is the original data, okay? The MNIST database of handwritten data sets, and these are kind of our original, the original authors and whatnot. This is their site. Jan LeCun, I don't know if you've heard of this man. He's a kind of famous machine learning person. Well, anyway, you would download these 4 files, okay? The images and the labels in the training set, the images and the labels in the test set, okay? But, the format of the data is these .gz files, okay? And so here I've downloaded the .gz file, okay? They're called, gzip files. And what you have to do is you have to unzip them, okay? And so that's on a Mac, you use the command gunzip or gunzip. And then on Windows, you probably have to download a piece of software. There's a free piece of software called 7-Zip, which I recommend. And then so for me, I've already done this, but I would just right-click. On Windows 11, you have to do show more options, and then actually I haven't installed 7-Zip on this laptop yet, but you'd use 7-Zip and do extract here, okay? And so you can see, this this compressed is around 9.6 megs, and uncompressed it's around 46 megs. So, and anyway, we're gonna get this loaded into R. So I've put in these two little scripts in the week 4 module, and so the neural network, R script, and a script just to kind of load the data. And so getting the data into R, requires a little bit of a little script, which kind of allows it to read this binary information. So we're not accustomed to reading in binary data, but you would need to read in binary data. And so this function load MNIST says it is going to look for these files, the MNIST training images .idx3ubyte data. And so the way I have it set up on my computer is I have I downloaded the R scripts into a folder, and within that folder I have another folder called MNIST. Now, if you decide to put the data files in the same thing, you might have to adjust the pathway to find the file. Okay, if you want to kind of follow along, and I think it's kind of cool to follow along because it's just kind of a fun and neat little data set. One of the question.
Sign-in is required to get the data set.
Really?
I don't know if it's just me. It's me too.
To download the data?
Yeah, to get into this website.
Let's see. If I click it, it just downloads. Wait, are you?
The website looks like this, like it won't show up.
Really? Okay. What? You're typing in yan.lacoon.com?
Mm-hmm.
That's so weird. How do you need a? Okay. You know what? Here. What if you just go to Google, and then you type in MNIST data, and then maybe the third link for me. The third link is the MNIST handwritten data set. Does that load up? Same thing? It's asking for a sign-in? Okay. What if you just hit OK? And you don't enter it? Okay, all right, you know what? We'll figure this, we'll figure something out. What if the Wikipedia page on this official website? Okay, well, all right. I'll have to check out what's going on your computers because I don't know. Okay, well, anyway, hopefully we'll be able to get the data downloaded. I'm sorry about that. And then we'll do show digit is another function. Okay, here, let me move, I guess, my face down there. All right. Okay, and so I'm going to just kind of run my script here. The first script, and so a lot of this is the same code that I showed you on Monday. So on Monday, we kind of went from the notes into the script, and basically it's almost the exact same script. I just changed the dimensions of the neural network. Okay. Oh, well, I guess there's a couple other things I need to maybe explain. So what the data looks like. Okay. So I load it, and it's a pretty big data set. Okay. And so the training data, okay, has basically these three elements. Okay, training data is a list, 3 elements. The first one is just there's 60,000. It's just an integer that says there's 60,000 images. Okay, and then there's an X and a Y. All right, the X is your input. The Y is the output. The X, what is this? This is a matrix. It is a matrix with 60,000 rows, 784 columns. Okay, and so what each image is it's a 28 by 28 pixel image. Okay, so each of these pictures, when we look at this this image here, each each of these things is a tiny little 28 by 28 pixel image. Okay. One of the reasons why the MNIST dataset is so popular is that it is a very clean data set, okay? In that all of the images are like, they're 28 by 28, and the numbers are pretty much somewhere in the middle of the image. So it's a very clean thing, whereas many other data sets, it's very messy, okay? And you don't have kind of this clean thing. So, kind of like the IRIS data set, there's kind of, it's just, you got these 4 columns and they're all numeric and it's very clean. You don't have other kinds of text or other stuff going on in here. And so 28 times 28 is 784, and basically they just took all 784 pixels and turned them into a numeric value. I want to kind of show you this animation from 3 Blue 1 Brown that shows what's happening here.
Carl's Jr. is spicing up the all.
Okay, we gotta endure a commercial for some fast food, some targeted advertising for me. Okay, all right. So this is what we're gonna have is in our input layer. Okay, so remember we have an input layer, a hidden layer, and an output layer. Within our input layer, we're going to have 784 nodes, for one for each pixel. In our hidden layer, I'm just, in this animation, he uses 2 hidden layers, but just for simplicity, I'm going to just have 1 hidden layer, kind of the structure that we created. And I just arbitrarily picked 30 nodes in the 1 hidden layer in the middle, I think. And then for the output layer, we will have 10 nodes, 1 node corresponding to each of the possible labels. So the digit can be labeled anywhere from 0 through 9. So there's 10 possible labels. And so we're going to have 10 nodes in the output layer. So 784 nodes in the input, 1 corresponding to each pixel in the 28 by 28 grid, 30 nodes in the hidden layer, 10 nodes in the output layer. 3 Blue 1 Brown, Grant has 784. He has 2 hidden layers, but again, just arbitrary choice, and then 10 nodes in the output layer. And he has this nice little animation and kind of explanation about what each of these things are. Okay, so let me just kind of play
let's
this.
break that down. What are the neurons, and in what sense are they linked together?
You know what? Let me, I'm going to pause the thing because sometimes when you play someone else's YouTube video, in your video that you post to YouTube, you get hit with copyright things, right? There's an algorithm that just looks for like video and sound recognition. So I'm gonna, so if you're watching online, look up this YouTube just video. It's 3 Blue 1 Brown neural network. But what is a neural network? Chapter 1, and fast forward to around 2 minutes 50 seconds, around 3 minutes into the video. Okay. Okay. So coming back from the video, we do something similar where we have 784 neurons in the input layer, 10 neurons in the output layer. The neurons in the output layer are going to go anywhere from 0 to 1. 1 indicating the neural network thinks it's very much that digit. 0 indicating the neural network doesn't think it's a digit. It's important to note that the values in the output layer are not probabilities. Okay, they are. We're accustomed to seeing 0 and 1 corresponding to probabilities, but they're not probabilities. They are just scores that the neural network gives to a thing that says, oh yeah, I think it's this number and I don't think it's this number. I mean, it is technically possible for the neural network to produce a number that's higher than 1 or a number that's less than 0 and things like that, depending on what kind of data comes in. And you can have multiple neurons that with high scores so that all of the values add up past 1. Or you could have multiple, all of the neurons can have fairly low scores where none of the values add up where the values don't add up to 1 and things like that. But anyway, just to kind of show you what this looks like, all right, so I'm going to just look at the first row here. And if we look at the Y, this is going to be the label, all right? And this says the number here for this first image is the number 5. And the digit itself, the training data, the input data, is 784 values, a vector of 784 values. Okay, so starting off with 0, and going up to 784 values here. Okay, and we can see some of these values have big numbers like 253 and things like that. And in 3 Blue 1 Brown's video, black pixels were 0 and white pixels were 1, and just on my image it's just the opposite. When I do show digit, we have 0 is a white pixel, and then the max value in our case 253 or 255 is a black pixel. Okay, and or did I say the opposite? I don't know what I said, but my images are just the inverse of what you say. And I think the 2, 3, 4, 5. I think the 5th image is the image that shows up in his video here. I think that was the example image that you see, right? And there's a few other images, so the second image is a 0, and you look at it and go, yep, that looks like a 0. The third image is the number 4, that's the number 4, and so on and so forth, right? And so we're going to do a couple things to get this input into our matrix. We're going to kind of scale all these values down. The raw data goes from 0 to 255, and we'll divide all the numbers by 255. Okay, 255 is basically the highest number you can represent with 8 bits, right? So with 8 bits, you have 256 unique values ranging from 0 to 255. So anyway, what I'm going to do is I'm going to turn the labels into a vector of zeros and ones. Okay, and so if the digit is the number 0, my vector is going to be a 1 followed by 9 zeros to indicate, because that first node corresponds to 0. If the digit is labeled a 9, it's going to be all zeros with the last value in the vector. So it's a vector of 10 zeros and ones. The last value is a 1, okay, and the other ones are zeros, okay? And so, a 2 would be 0, 0, 1, 0, 0, 0, and so on and so forth. So what I'm going to do is I'm going to kind of vectorize. So basically, vectorize just creates a vector of 10 zeros, and then it puts a 1 into the basically the label plus 1 spot. Okay, so that's what it's going to do, and then we apply that to our data, and then we can kind of just see, so this first value is a 5, and so we have 0, 0, 0, 0, and then a 1 in the node that corresponds to a 5, which is the 6th node, and then 0, 0, 0 for the other 4, and so on and so forth. Okay, the second digit is a 0, and so we have a 1 in the first node, and then zeros everywhere else. Okay, so this is where things like, because R is a 1-indexed language versus a 0-indexed language like Python, it's like, oh yeah, I got to add 1 and stuff like that. Okay, and then so anyway, we can kind of just show the digit for, I guess that 4th image here, or the 3rd image. Okay, and then so now I'm going to just kind of input some of the other functions. Okay, so here I have the sigmoid function, sigmoid prime function, the cost function. So these are all just straight from the neural network code that we kind of created or looked over in Monday's lecture, right? So we, in Monday's lecture, I said, all right, here's the kind of the math that we did, and then now we're turning it into code. And so this is the exact same code that I use there. I'm using the same instructions here where it says input layer size, output layer size, hidden layer size. Okay, and here I'm saying the input layer has 784 nodes, the output layer has 10 nodes, and the hidden layer has 30 nodes. Okay. And then, and so now, I guess if you think about the first weight matrix, I have 784 nodes in the input layer and 30 nodes in the hidden layer. So I'm going to have 784 times 30. So I'm going to have, how many values? 23,520 values in my weight matrix, right? It's going to be this kind of this big weight matrix, 784 by 30, 23,520 values, right? And so training our neural network means figuring out what weights to use. There's a lot of weights to use here, okay? And so we're going to try to figure out what weights to use for these 23,000 values in that first weight matrix, and then we're going to have like another 30 by 10, another 3,000 values in the second weight matrix. So my first weight matrix, okay, I'm just saying pick some random numbers, initial random numbers for our initial weights here. And so I'm saying RUnif, how many values do I need? I need 23,520 input layer times hidden layer. And then RUnif generates values between 0 and 1, and then so I'm just shifting it down by half, so it's going to be random values between negative 0.5 and positive 0.5, okay? And so I'm going to do that for the first weight matrix, W1, and then I do the same thing for W2. And you can see, you know, W1 is a matrix 784 by 30, W2 is 30 by 10, okay, which makes sense, right? Okay. To train our data, train our neural network, I have 60,000 images. And so my training data, okay, is this huge matrix, 60,000 rows by 784 columns. And if I were to kind of run that through my matrix and do gradient descent, it would cause my computer to, you know, like slow down a lot, or not slow down. It would just take a lot of computational energy. So we're going to do something called stochastic batch gradient descent. And what that does is rather than looking at all 60,000 and processing all 60,000 all at the same time, we're going to just divide it up into just tiny little packets, okay? And we're going to do 6,000 batches of 10, okay? And so each kind of training data point is just going to be 10 little images, okay? 10 images, and then we say, okay, calculate the gradient for these 10 images. So remember, when you do gradient descent, you take your input data and you say, okay, what are the predictions that you're making on the input data? And then what's the loss, and you know, how do we kind of point the arrow you know, downhill for this particular set of images, all right? And so, you know, basically, if you remember, how do we calculate the gradient and whatnot? There's like this big summation sign, right? It's the sum of, basically, you take one input row and you calculate basically the gradient for that thing, and you kind of add it to like the next input row and so on and so forth. But you know, we use some matrix multiplication, so it all kind of gets added in there. So basically, you know, instead of doing a summation of basically 60,000 images, I'm just going to do a summation of 10, and it's like each of those images gets like one little vote as far as like which way is downhill, right? So the first image says, oh, okay, the gradient downhill is pointing in this direction. The second image says, oh, you know, downhill is pointing in this direction. The third image says, oh, downhill is pointing in this direction. And you kind of just add all three of those, you know, different vectors, and you get kind of like a downhill direction, you know, somewhere in between all of those images. And so, so to kind of do stochastic batch gradient descent, what I'm going to do is I'm going to take the 60,000 images, I'm going to just shuffle them up, and then I'm going to create little batches of 10 images each, and we're going to have 6,000 of these batches to go through. Okay, and I could repeatedly iterate, but I'm just going to go through all 6,000 batches exactly once. So I'm just going to use the 60,000 images. Each one just gets you know, just gets cycled through once, and we could run the thing loop multiple times, but I think it's fine. Okay, so here I'm gonna set the seed. I'm gonna say I've got 60,000 images. I'm gonna just arbitrarily choose a batch size of 10. I'm gonna shuffle those 60,000 images, and then now I have a bunch of kind of little batches of 10. Okay, and this is the gradient descent algorithm. And, I don't know if your brain just glosses over code or if you kind of read through it line by line. And my hope is we're able to read code a little bit and just kind of see what's going on, right? So this first part just says, okay, what we're going to do is these are the rows we're going to select. We got 10 rows. And so my input matrix is going to be, I'm going to subset to those 10 rows that I've selected, the 10 in this current batch. And then I'm scaling them down. I'm dividing all the values by 255. So all of my values are between 0 and 1. Okay. And then we're using the labels, the output. This is our the targets that we want to hit. Okay. And the targets are zeros and ones, right? So I've got 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay. And when we measure our loss, our neural network's going to produce a vector of 10 values, okay, because there's 10 nodes in the output layer. And so our neural network produces a vector of 10 values. And so, in the beginning, it might predict like 0.8, 0.7, 0.2, 0.1, 0.6, and something like that. And it's going to start off and say, this is really bad, right? Because 0.8 from 0 is far, 0.7 from 0 is far, and 0.6 from 0 is far, and 0.2 from 0 is pretty far. And then we have a 1, and maybe it's predicting a 0.5. And basically, what it wants is if the output is 0, it wants the output of the neural network to also be something close to 0. It's probably not going to be exactly 0, but maybe 0.0002. versus 0, and that would be great, right? And then if the node is a 1, we want our neural network to predict something close to 1, maybe 0.99 versus 1 or 0.97 versus 1, and that will have a small loss, okay? And so our output layer, we got a vector of 10 things, and we're gonna, find the outputs for those 10 rows that we've selected. Whoops. Okay. Well, actually, I'm not running this. I will run when I do this. Do this for loop, okay? And then we do forward feed. So we take our input matrix X, it's 10 rows, 784 columns. We multiply it by our W1 matrix, 784 by 30 weights, okay? That gives us our Z2 values. We run our Z2 values through the sigmoid function or the logistic function to get our activated values in the hidden layer. We take those activated values, multiply it by the second weight matrix to get kind of our Z values, and then we run those Z values through the sigmoid or logistic function again to get our predicted values. So this is just doing forward feed to get our predicted values. And then we calculate the gradients, okay? And so this is just the code for the gradients, which is, we went through the work, I guess last Friday to do the back propagation to get the gradients. And so this is the code there. And then once we have the gradients, we just do gradient descent, which is take our current values, our current weight matrix, and subtract off some scalar value times the gradient, right? Is that okay as far as the code for gradient descent? So we will go ahead and run that. And so let me just kind of run through all of this. And then, so we run through this. Oh, I forgot. I should give you view quiz answers, huh? Okay, I gotta log in because I don't remember what the answers are. Oh, okay. So okay, well, it's done. It's the training of the neural network is done. It has gone through all 60,000 images, and it has used that to figure out what the direction downhill should be. Okay, and it has followed it, and let's see how it performs. Okay, all right. So so what we're going to do is we have our test data set. Our test data set has 10,000 images, and we're going to try. So in our neural network has not seen any of the images in the test data set. So we're getting like new handwritten digits, and we're saying, okay, neural network, can you give me a prediction for what label this image is? Okay, so so I'm going to take my test data and I'm going to scale them divide them by 255, and then here we'll just take one image, okay? And so, and I'm going to feed them through my neural network. So now my neural network is trained, so this W1 matrix has the values it needs to make good predictions. That's all training the neural network goes, right? This W1 matrix has a whole bunch of values in it, and we just said, okay, let's figure out right? I started off with some random values, and then we said, okay, neural network, do gradient descent and tweak the values in here. And it said, okay, I tweaked the values in here. And so, I mean, we can look at like some of the values in W_1. Let's just look at like the first 3 rows and first 3 columns. And it's like, okay, this is the weight going from the top, I think this is your top left pixel going to this hidden layer. But again, what does this mean? It means absolutely nothing, okay? That's the downside of the neural network, is that you get these weight matrices and you're like, okay, but again, they are completely uninterpretable. And the only way we know it's working is by we give it test things and it says, okay, can you identify the letter? And if it can, you're like, okay, great, you learned, right? And it's kind of like, when you teach a kid how to read, recognize letters, it's not like you're gonna look inside their brain and go, oh, you formed a good connection between these neurons in your brain. You just go, okay, what letter is this? The letter A. Good job, right? You're learning, right? And that's all we're gonna do. We're gonna just say, okay, tell me what this is, and go through and tell me what your guesses are, okay? So to get the guesses, remember our y-hat matrix, the predictions are these vectors, okay? So here I can just say my prediction, y-hat, let's look at the first row, case sensitive. Okay, so the first row, I have 1.86, 10 to the negative 4. What is the prediction here? So it'll be easier if I round it, okay? So let me round to, say, 2 decimal places, okay? And so we can see, these get rounded, maybe if I keep 5 decimal places there, right? So when I round them, these are really small values, 0.00019, 0.0000, 0.020237. So most of these are very close to 0, okay? And then we get one value that's 0.99978, and then the rest of the values are very close to 0. So this would correspond to this one's a 987. Okay, so this corresponds to a 7, and we go, okay. So that's what it's doing. And so all I've done is to get our guess, I just said, hey, what is the max? Which column has the maximum value? And then again, because it's 1 indexed, we're going to subtract a 1 from it. Okay. So my guess for this digit is a 7, and then let's plot what that image looks like. And what we want is a thing that looks like a 7, right? So this is the big reveal. Did it work? And then we go, oh yeah, okay, good job, neural network. That's a 7, and it has recognized it, right? So again, we don't really know what's happening, but all we know is that when we gave it this image here, the neural network went through and said, do I think it's a 0? This is how much I think it's a 0. Do I think it's a 1? This is how much I think it's a 1. Do I think it's a 7? This is how much I think it's a 7. So we're going to say, I think it's a 7. Okay, I'll just, let's just go ahead and give you all 3 ViewQuiz answers, okay? The answers are C as in cat, followed by D as in dog, followed by A as in apple. Okay? Cat, dog, apple. C, D, A will be your 3 ViewQuiz answers for today. Okay, so let's try out the second one, right? So our second guess is a 2, and again I can ask what did numbers look like, and so you can see sometimes this output for the number 2 wasn't a 1, it reached a 0.8862. Okay, so it wasn't as confident, but it's, and again, these numbers don't even add up to 1. And again, it's not a probability. There's nothing. It's just trying to get something. So, let's just see what is this. And yeah, okay, that's a number 2, right? What about the next one? Okay, it's guessing a 1. And yep, good job. Okay, and we can kind of go through. This one's guessing a 0, and that looks good too. Okay, so I'm going to create something called a confusion matrix. Okay, a confusion matrix is going to. I've got 10 possible values for what the answers are, and we have the truth, and we have the neural network's prediction. And so what we want to see is we want to see lines down the diagonal, right? We want to see values down the diagonal. That's when, if the true value is a 0, the neural network guesses a 0. Okay, if the true value is a 1, the neural network guesses a 1. So what we want to see is, when the true value is a 0, we want to see a very high number for guessing a 0, and very few numbers for guessing a 1, 2, 3, 4, or something else. Okay, and then if the true number is a 1, we want to see the neural network guessing 1 many times and guessing other numbers very few times. So here I say the actual will be the actual labels in the test thing, and then the guess will be equal to a guess. Okay, so I table up these results. Okay, and so this is what the so if the actual value is a 0, we guessed 0 941 times, and we guessed the number 1 0 times. We guessed the number 2 10 times, and the number 6 got guessed 21 times. And that kind of makes sense, right? When you think about what does someone's 0 look like and what does someone's number 6 look like, we're like, oh, okay, I can kind of get that, right? And then for the number 1, we guessed 0 times. We guessed 1 1,113 times. We guessed these other numbers, a few times. And so we do see quite a few values along the diagonal. It seems to have I don't know which one has the lowest accuracy rate, because each row doesn't sum to the same number. But yeah, we do see, overall, it looks kind of successful. So, what I'm going to do is I'm going to just take the values along the diagonal and just divide by 10,000, okay? And, we're achieving around 92.5% accuracy, which, in my opinion, is pretty good, okay? It's pretty good. Not great, okay? It's not great, but this is a very simple neural network, right? We just have one hidden layer, and there's 30 nodes in the hidden layer, right? And and we didn't even use bias values. And so there's a few things you could do to your neural network. You could add a few more hidden layers. You could add bias values, give it a little bit more flexibility. You can train it for longer and things like that. And you'll probably improve your accuracy a little bit, but not so bad. And even if we don't fully understand all the values inside the weight matrix, my hope is that the code that got us here to get us 92.5% accuracy, we can read and understand this code. It's not some mystery black box where it's just okay, computer, do this, and then the computer does it. But rather oh yeah, these are just matrices, right? We created the matrix ourselves. We wrote the sigmoid function here. We understand what's going on. We derived what the gradients are, and we used gradient descent to train the network, to help figure out what values to use in those weight matrices. And so my hope is that this at least removes some of the mystery of what's happening in a neural network, at least how we're arriving at the weights used, and then and so that's basically what's happening. And pretty much, deep learning is just this exact process, but just on a much bigger scale. All right, it just has more nodes, a lot more layers, but all it's doing, and a lot more data, and it's feeding in a ton of data, and it's using that data to use gradient descent and figure out what weights to use, and that's what the training process is. It's just figuring out what weights to use, and then once it's got the weights there, it says, okay, give me a picture, and I can tell you, oh, it's a picture of a bus, or it's a picture of a stoplight, or something like that, right? And when you get prompted on your phone and it says help, which of these images contain pictures of traffic signs and things like that, what you're doing is you are providing data to help train the neural network. Okay, so it's kind of this funny little engineering thing, but basically, like some of the things they know the answers to, and some of the things they don't know the answers to. Okay, and so if they use the answers that they know to help detect whether you are a robot or a human, and then the answers that they don't know, you are providing, and they're using that to train their basically self-driving cars and stuff, right? So when you click the images on your phone to say I'm not a robot, you're basically providing the answers for what images contain bridges and stuff or whatever it is, right? So that's why all of the things are probably traffic related these days as far as images and stuff, right? Because they have a bunch of data and they need somebody to label it. So why not ask you to label it for them, right? Okay, let's take a look at some of the things that the neural network got wrong. And so I'm going to just say, hey, where did the actual not equal the guess, okay? And so we can see some of the images that it labeled wrong. So here it labeled image 9 incorrectly. Okay, so let's just take a look at that. And so the label is a 5, and then we say, okay, well, what did it guess? It guessed a 6. Okay, well, let's see what this digit looks like. Okay, so this is someone's handwriting, and we go, oh, okay. You know what, neural network? I'm not mad at you. You thought this was a 6. Okay, it turned out to be a 5. We're not angry, right? We understand. Okay, we're angry at the person who wrote this, right? And the reason why they know it's a 5 is because they have other information on like the postcards. It'll say like, oh, this is going to San Jose, which has a 5 in its zip code or something. I don't know what San Jose zip code is. I'm just making that up, right? So they have other information, and I think a human might say, oh yeah, that looks kind of like a 5 too. Okay, here's another number. Oh, it's another 5. Okay, it guessed a 3. Let's see. Oh, okay, we go. All right, that's a 5. That's clearly a 5. Neural network, maybe not so great. But you also kind of understand how the neural network could have thought it might have been a 3 or something like that. So, and then you can kind of go through any of these other things that it got wrong, like image 9987. Let's just kind of see what 9987 looks like. Okay, the label's a 3. It guessed an 8. And we go, oh, okay, So again, some of these images, it's like, okay, that's clearly a 3. But then we also maybe could understand how it could mislabel some of these things. And again, it's a very simple neural network design that we used, achieving around 92.5% accuracy. But anyway, my hope is it kind of makes sense how we train this, and so yeah, you can kind of play around with this. But okay, so we'll go ahead and end here, and then I want to kind of see what's going on with your computers to see like why we can't access the website and download the data. So I don't know. I was under the assumption that everybody could download it. Okay. All right. Well, have a great weekend, and we'll see you next week.